As an example for Faraday's law for the induced electric field, we see in this figure we have magnetic field inside a circle of capital R, and this magnetic field has a rate of change of magnetic field delta V over delta T equals 0.13 Tesla per second, and the area or the radius of the circle, which includes the magnetic field capital R, equals 8.5 centimeters. And it is required to find out an expression for the magnitude of the electric field of the induced electric field at a point within the magnetic field. So we want to find the electric field for a point inside the magnetic field at a radius r from the center of the magnetic field. So we are saying inside, so r here is smaller than capital R. Okay? And evaluate this value for r equal 5.2 centimeters. So in this case, we are going to find out the electric field at a point small r, which is smaller than or equal capital R. So in this case, we say that the integration over a closed loop of the electric field dot ds to the distance would equal minus partial phi b by partial t. And phi b is the total flux which passes through this loop. So phi b in this case would be the magnetic flux B multiplied by the area of the circle with a small r. So phi b in our case is B multiplied by the area, B equal B multiplied by pi r squared. So the integration of the electric field over a closed loop ds would be minus partial phi b by partial t. And actually the integration on this closed loop equals the value of the electric field E multiplied by the circumference of the circle of small r. So this actually is E multiplied by 2 by r. Now let us take the integration of E dot ds over closed loop to be E multiplied by 2 by r equals minus the rate of change of the magnetic flux with respect to the time. So would be minus partial by partial t b multiplied by r squared. By r squared is constant. So this partial b by partial t, and it is given that partial b by partial t is 0.13 Tesla per second. So in this case, the electric field E would be this value over 2 by r. So this pi will be removed with this pi. This r will be removed with the square, and 2 will be in the denominator. So the electric field in this case equals r over 2 multiplied by partial b by partial t. Now let us apply with the numbers. We have r here is 5.2 centimeters. So it is 5.2 multiplied by 10 to the power minus 2 over 2 multiplied by partial b by partial t. Partial b by partial t is 0.13 Tesla per second. So the electric field or the induced electric field in this case is 0.0034 volt, or in other words, it is 3.4 millivolt per meters. It should be noted that the electric field inside the region of the magnetic field itself, the electric field is proportional to the R. So as long as I am moving from the center of the region of the magnetic field, the electric field is increased linearly. Okay? Now the question is, what will be the electric field outside the loop of the magnetic field? As we mentioned, if I'm talking about a closed loop outside the region of the magnetic field, the integration of the electric field on this closed loop would be zero. But this doesn't mean that the value of the electric field is zero. Alright? So we are going to make a closed loop outside the magnetic field, and we say that the integration of the electric field dot ds would equal minus partial phi b by partial t minus the rate of change of the magnetic field inside this closed loop. So for any point outside capital R, the magnetic flux is the total magnetic flux, in this case, inside this yellow area. So the magnetic flux here would be B multiplied by the area of the magnetic field, not the area of the electric field. Because the area of the electric field, this part, for example, doesn't include magnetic field. Okay? So the total magnetic flux in this case would be B multiplied by A, where A is by capital R squared, which is the area which includes the magnetic field. This is the magnetic flux. Now, the integration of the electric field dot ds would be E multiplied by 2 by R. Here small r is greater than capital R. It is outside. So in this case, we say that the integration of electric field dot ds on a closed loop would equal minus partial phi b by partial t. So in this case, we say the electric field would be the differentiation of phi b with respect to t, which is by capital R squared multiplied by partial b by partial t over 2 by r. So this pi will be removed with this pi, and everything will be remain capital R squared over 2r multiplied by partial b by partial t. So in this case, if I'm looking for the electric field outside the area of the magnetic field, I can find out it is inversely proportional to the radius r outside. So if I'm going to draw the electric field, if I'm inside the region of the magnetic field, the electric field was proportional to R. If I'm going outside the region of the magnetic field, the electric field will be proportional to 1 over R. Okay? Now we are going to apply for value R equal 12.5 centimeters and capital R was 8.5 centimeters. So the electric field in this case would be 8.5 multiplied by 10 to the power minus 2. All of this is power 2 over 2 multiplied by R. R here is 12.5 multiplied by 10 to the power minus 2. This is multiplied by dB by dt. So this multiplied by 0.13 Tesla per second. the induced electric field in this case would be 3.8 millivolt per meter. Okay?